Anyone who's ever wrestled with AC circuits knows it can get complicated and fast. We're talking about a sea of messy sine waves and some really tricky trigonometry. But what if I told you there's an elegant shortcut, a way to turn all of that chaos into simple, clean arithmetic? Well, today, that's exactly what we're going to dive into, the incredibly powerful tool known as the phasor.
And believe me, it is so easy to get lost. As this little note from MIT points out, just keeping track of the pluses and minuses in AC analysis can drive you crazy. But the tool we're about to explore is designed to just slice right through all that confusion, giving us a clear, almost intuitive path to the right answer every single time.
So what is the core problem we're actually trying to solve here? You know, it all boils down to it sounds like a really simple question. How do you add AC voltages together? As you're about to see, the answer is, well, it's a wave of complexity.
Okay, first, a super quick refresh. That AC voltage, the kind that's coming out of your wall sockets right now, is made by the circular motion of a spinning rotor inside a generator. And it's that constant, smooth rotation that naturally creates a voltage that rises and falls in that perfect, predictable pattern we call a sine wave.
Okay, so in the real world, circuits are rarely that simple, right? You often have multiple things in a circuit, creating multiple voltages. So what happens when you try to add two of these sine waves together?
Well, let's take the easy case first. If the two waves are perfectly lined up, what we call in phase, the math is as easy as you'd hope. See? The peaks line up, the valleys line up. A 3-volt wave plus a 4-volt wave just gives you a 7-volt wave. Easy peasy.
Yeah, but when are things ever that easy? What happens if they're not in sync? You know, what if one wave is just a little bit delayed or phase shifted? Well, that's where our simple addition completely falls apart and things start to get weird.
And this is where your brain starts to hurt a little. We've got our same 3-volt and 4-volt waves, but now one is shifted by 90 degrees. When you add them up point by agonizing point, the new wave that you get peaks at 5 volts. That's right, 3 plus 4 equals 5. Now that feels completely wrong, but that little 3-4-5 relationship, that should be a huge clue. There's some hidden geometry going on here, and it's screaming that we need a better way to look at this.
All right, so to solve this, we have to do something kind of radical. We need to completely change how we even look at a sine wave. The key is to stop thinking about them as complicated, squiggly lines on a page. We need a new perspective. We need to shift from thinking in lines to thinking in circles.
And here it is. This is the big idea. A sine wave isn't just a graph. It's really just the projection, kind of like a shadow, of a point that's moving in a perfect circle at a constant speed. You see, as that point spins around and around, its vertical height, its shadow on the wall, traces out that perfect sine wave. This is the whole key.
So what does that do for us? Well, this one mental leap completely reframes the problem. We're no longer adding these incredibly complex waves. We're now just dealing with simple spinning arrows, or vectors. The length of that arrow is our peak voltage, and its angle tells us everything about its phase.
Okay, so we've got these cool spinning arrows, but we need a way to talk about them, right? Mathematically. We need a type of number that can capture not just its length, but also its direction. And this brings us into the fascinating world of complex numbers.
And that, my friends, is where the hero of our story comes in, the phasor. That's exactly what it is. A phasor is a special kind of complex number that beautifully packages up the two most important things about our sine wave, its amplitude or magnitude and its phase angle, all in one neat little number. So how do we map these things? We use something called a phasor diagram. It's basically a special grid. The horizontal line is the real axis and the vertical one is the imaginary axis. Just think of it like a GPS for our sine wave. The position of our little arrow on this map tells us everything we need to know at any given moment. And we can describe a phasor's position in two different ways. Rectangular form is like giving someone directions using grid coordinates. Okay, go west about 208 steps, then turn and go north 120 steps. But polar form is often way easier. It's like saying, just face 150 degrees and walk 240 steps. They're two different languages describing the exact same spot.
All right, so we've done the setup. We have this new way of thinking, this new mathematical language. Now for the payoff. How does all of this give us that elegant solution to the messy problem we started with?
Let's go back to that head-scratcher from before. But instead of seeing two messy sine waves, we now see two simple, beautiful phasors. One is a 4-volt phasor pointing right along the 0-degree line, and the other is a 3-volt phasor pointing straight up at 90 degrees.
And just look at what happens now. This is the magic. We're not adding an infinite number of points on a curve anymore. We just add the two arrows together, tip to tail. It's basic vector addition, and in our case, the two arrows form a perfect 3-4-5 right triangle. The problem just solved itself, visually.
A little bit of high school geometry, the good old Pythagorean theorem, tells us the length of that new arrow, the result, is exactly 5. And the angle, a little under 37 degrees. We've just found the peak voltage and the phase shift of our combined wave with math you learned in 9th grade. That's the power of the phasor.
And you know what the best part is? You don't even have to do the geometry yourself. Any modern scientific calculator can handle complex number math without breaking a sweat. You just punch in the two phasors, hit the plus button, and boom, it spits out the right answer instantly. That entire, messy, confusing problem is literally reduced to a single button press.
Okay, so this is obviously a really cool trick, a neat shortcut. But why does it matter so much? Why is this considered one of the most fundamental bedrock concepts in all of electrical engineering?
Because this isn't just a party trick for adding two waves. This is the foundation for pretty much all modern AC circuit analysis. It's what allows engineers to take fundamental rules we use for simple circuits, like Ohm's law and Kirchhoff's laws, and apply them to vastly more complex AC systems. It is absolutely essential for everything from designing our national power grid to the signal processing happening inside your phone.
It's like the author Tony Kupfalt says, phasors are so powerful because they let us treat these complicated oscillating AC quantities with the exact same ease as we treat simple, steady DC quantities. They tame the complexity.
You know, when you really think about it, the story of the phasor is about so much more than just electricity. It's a perfect example of how a problem that seems impossibly difficult can become simple, even beautiful, if you can just find the right way to look at it. It really makes you wonder, what other complex problems out there are just waiting for the right change in perspective?